right, everybody, welcome to the video for lesson number 6's homework assignment. I'm hoping that you've done this already before you're watching the video, so you're just kind of checking your work. So the first question gives us a polynomial, p of x, which is graphed. Tells us we don't need to factor this question to be able to solve it, which we don't, because we know about the graphs and what the graphs tell us. So a couple things we have to see here. I see that this has a degree of 5. This is a 5th degree polynomial, meaning there are 5 total solutions. Now, some of these solutions can count more than once, some of them could be real, some of them could be complex. I don't know until I look at the graph. So it says, how many linear factors is p guaranteed to have? By the fundamental theorem of algebra, the degree tells you how many factors. So there has to be 5 factors. And we know that because it's a 5th degree polynomial. How many real zeros do we have? Remember, real zeros are x-intercepts. There are 1, 2, 3 x-intercepts. So I can say there are 3 real zeros. They don't even want you to say which ones they are. I just want to know how many. So if there are 5 total zeros or factors and 3 of them are real, that means the other 2 must be complex. So there are going to be 2 complex zeros because there are 5 total zeros and 3 are real. Then it says, what do we know about the complex zeros? The 2 complex zeros are conjugates. Remember, conjugates would be like 2 plus or minus I, one and the other, right? This would be like an example of a conjugate. All right, number 2 says find all of the zeros. This is a factored polynomial for the most part. There's one piece we do have to factor. So let's factor everything we possibly can. So if we factor over the complex numbers, x squared plus 4 becomes x plus 2i, x minus 2i. X squared plus 1 is x plus I, x minus I. X cubed plus 8, that's sum of 2 perfect squares, or in this case, difference of 2 perfect cubes, something like that, right? It's cubes. So we can say x minus 2, x squared plus 2x plus 4. That is just factoring from unit 1. We should know how to factor that. The last 2 are already ready to go. There's nothing to do, so we're just going to leave them as is. So there are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 solutions. This is a 9th degree polynomial. We've now set it equal to 0, so we can find the zeros. So I'm going to get a 0 of negative 2i, positive 2i, negative I, positive 2. This one we'll do it later. This one's negative 3/2. Subtract 3, divide by 2. This one's positive 4/3. Add 4, divide by 3. Now there's one that I skipped here. The reason why I skipped it is this is not factorable. We have to use a quadratic formula. So once we have this all set up in the quadratic formula, we want to try and evaluate it and solve. So if we find the value of the discriminant, we get negative 12, telling us there's 2 complex zeros there. Square root of negative 12 is going to become I square root of 12, which is going to become I and 4 times 3, or 2I square roots of 3. So now that I've done all that work off to the side, let's put it back in. Negative 2 over 2 plus or minus 2i squared to 3 over 2. So negative 1 plus or minus I squared 3. So let's write a solution set here, a final answer. What are all the zeros? Let's put the real ones first. So I have 2, negative 3/2, and positive 4/3. complex ones. And I should have 9 total. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow, that's a lot of work. But we can do it. It's just a lot of things that we all have to put together. All right? Next one. Gives us a polynomial. Wants to determine what are the real zeros of p. So this question I'm actually asking you, what are the zeros? All right, so here's one, here's one. So the real zeros are -1 and +3. So since this is a degree 4 polynomial and 2 zeros are real, that means there are 2 complex zeros. Right? The number of real zeros plus the number of complex zeros has to equal the degree. Part C says factor p using the zeros from the graph. So we have to first divide out one of these factors. So if we take this polynomial and divide out a factor, so if we take, let's start with x plus 1, right? So if -1 is a 0, x plus 1 is a factor. I am trying to recreate x to the 4th. I'm trying to recreate -6x cubed. I'm trying to recreate 11x squared. And 0 x's. So if we put in what we now know, this should be x cubed, which will make this x cubed, which will make this -7x cubed, to make -6. -7x squared, which will make this -7x squared. But I would have to add to 18x squareds to make a +11, to make this 18x. And that would make this 18x. But I want 0x, so that would be -18x. -18, -18. We like that because that should be the same number as the last number of the polynomial I'm dividing by, which it is. So from this first step, I can say p of x is equal to the factor x plus 1 and x cubed minus 7x squared plus 18x minus 18. Unfortunately, that cubic I just created is not factorable. So I need to do another division problem. But this time when I do my division, I'm going to use the other factor. So the other 0 was +3, meaning the other factor is x minus 3. And this time I don't want to create the original polynomial. I want to recreate this one. I want to take x minus 3 away from that one. So I want to create x cubed. I want to create -7x squared. I want to create 18x. So that would make this x squared, -3x squared. -4x squared, that would make -7x squared, so we're good there. Minus 4x, that would make this 12x. I need that to be 6. That's 6. -18, which is good. So what this tells us is now I can write p of x as x plus 1, x minus 3, and this new expression, x squared minus 4x plus 6. That last one, does anything multiply 6 to make -4? The answer is no. So the only way to factor this last one would be using complex numbers. So we're good. We're done. Right? I don't have to go any further than that. Now it does say to find the zeros. Well, we already know 2 zeros. One of them is -3, one of them is +3. So if we go through and solve the quadratic formula for that quadratic here, we should be able to find the other zeros. Off to the side, let's find out what this discriminant is. The discriminant comes out to be -8. So we want to simplify that. So we have 2i squared 2. Break it up. Right? Remember in algebra algebra 2, we like these as two separate fractions. Simplify. There's my complex zeros. So since it says find all zeros, we have to state all the zeros as a solution set. So I'm going to have -1, 3, 2 plus or minus I squared of 2. That's my answer for all zeros of this function. Hopefully that helped with your homework. Hopefully you'll do a lot of that yourself, and I will see you soon.